general setup is the following. So if we have base B, so we have base B. So we have base B. Okay. We have our standard base E. So we have our standard base E. And when we have our matrix P, so P is from B to E. Right here, B to E, and P inverse E to B. Okay. If we have T as a linear transformation, then we can have matrix A for T in base E. That's matrix of T in base E. And we also can have, say, matrix of T in base B, right? So we can write down the linear transformation in two different bases, base E and base E, base B and base E. So then the connection between these two is going to be the following. So we have A is E. So we want to have transformation of matrix transformation A and E. That's equivalent of doing the following. To go from translate our language. So right now, if we start with X, we will assume that is given to us in base E in standard base. So we kind of interpreting it now in language of base B. So we're doing from E to B, which is in our case is called P inverse. Then we do transformation. In that new language B, okay? And then we're doing back to our normal language standard base, okay? So think about that like you're translating to the language. So we did translation from English to say to French. We did something in French. And then when we got conclusion in French, we translated back what was written in French back to English. So we did from English to French. We did whatever we need to do in French language because for some reason it was easier to do it there. Then conclusion, only conclusion was translated back to language in English, okay? So that's what we're going to be using, okay? And that's where the similar matrices are coming to be important, okay? So what basically the similar matrices will tell you that, you know, it's the same linear transformation, but written in different bases. So if you remember, if you have eigenbase, then the correspondence, so B is eigenbase. Then eigenbase, say, of transformation T. Then transformation T written in base B is going to be linear matrix. And it's easy to work with diagonal matrices. Okay, so that's the reason we want to have eigenbases if possible. Okay, so now let me try to illustrate example. Maybe it will be easier to show you what I'm trying to tell you in one example. So just imagine we have T, which is linear transformation from R2 to to R2. So we have linear transformation of two-dimensional plane, and it does the following. So we have our XY plane. We have a straight line y equals to x. And what that linear transformation does, it takes a point and it moves it around that straight line y equals x. Okay, so it takes that point and moves it here. Takes this point and moves it somewhere here. So it reflects points around straight line y equals x. Okay, so it reflects points around straight line y equals to x. So what we want to do is find the matrix. Okay. And if you know matrix of T, we should be able to calculate and do whatever we can do with linear transformation. Okay, so we can, after that, we can ask all kind of different questions like what's the image of this point, what's the image of that point, and so on and so on. Okay. Let's see how we're going to be working with this one. So let's have a look. So what we're trying to do is we want to try to find eigenbase. Okay, and in this case, it's kind of eigenbase of T. So let's try to find it. We can visualize it, right? So if you just imagine, if you have that vector which sits right on the line, right? Then that vector which sits right on the line reflects into itself, right? So let's call this one U1. So G of U1 equals to U1. And because we have straight line y equals to x, then we can choose U1 to be a vector with coordinates 1 and 1, because y equals to x is a straight line, right? Then we also can pick another vector, which is going to be perpendicular to the axis around which we flip. So we want to have 90 degrees here. That's U2. And T of U2, because it's perpendicular, so it will go to opposite direction. So it's going to be negative U2. Okay. And if you like, you can eyeball here that U2 is going to be negative 1 and 1. Right? Because the line perpendicular to straight line y equals to x, you can kind of play with it. So what we see is U1 is eigenvector with lambda equals to 1, and U2 is eigenvector with lambda equals to negative. So we have eigenbase now. Okay, so we're working with base B, which is going to be U1 and U2, and that's going to be eigenbase. And as soon as we got eigenbase, it's easy to write down our transformation in that eigenbase. So T written in base B is going to be where U1 goes and where U2 goes. T of U1 is U1, so 1, 0. T of U2 is negative U2, so 0 minus 1. Okay, so it's going to be easy to us to write down the matrix for T in terms of eigenbase. Now, again, B is 1, 1, negative 1, 1. Then our P, which going from B to E, is going to be 1, 1, negative 1, 1. And we're going to call it P. And P from E to B is going to be inverse of B to E, so it's going to be P inverse. And now transformation T, if we want to write it in base E, is going to be, we start with base E, so we want to switch it to from E to B. So we switch into a base. Then now we are working in base B, so we're working in language B. So now we can find transformation T in that base B. So now we're in base B, and we already did the transformation, and now we have to go back to the original base. So we're going from B to E. Okay. So in terms of our language, that's going to be P, T, B, P inverse. We know what T is in base B. You remember it was right here. 1, 0, 0, minus 1. We know what P is. All that is left is find P inverse. So 1 minus 1, 0, 0. P is 1 minus 1, 1, 1. And all that is left, just find P inverse. That's the only thing which is left, but to find P inverse. We write it down 1, 1, 1 minus 1, 1, 1, 0, 0. So that is P, that is E. And then we want to change P into identity matrix. And whatever is written on the right side was the best track is going to be eventually our P inverse. So we do say row 2 plus row 1. So we're going to get 1, 1, 1, 0, 2, 0, 1, 1, row 2 divided by 2. So we're going to get 1, 1, 1, 1, 0, 1 half, 1 half, 0. Then row 1 minus row 2. So we're going to get 1, 0, 1 half, 1 half, 1 half, negative 1 half, 0, 1. Switch row 1 and row 2. So we're going to get 1, 0, 0, 1, 1 half, 1 half, minus 1 half. So that is P inverse. And now we're ready to write down T in base E. It's going to be P 1, 1, 1 minus 1. T in base B, 1, 0, 0 minus 1. P inverse, 1 half, 1 half, 1 half, negative. So that is P, T in base B, and P inverse. Okay, so that's going to be final answer. Well, of course, we'll do calculation, but that's about what we're looking for.